Good morning, class. Here is an example of exponential functions. So let's do that next. Um, Last time we talked about inverse functions. Let me quickly do one idea, further creepiness with inverse functions. Let's talk about composing functions. We've talked about composing functions a couple sections ago. If you compose a function with its inverse, the answer or output will always be the initial input. For example, let f of x equal x minus 2 and let g of x equal x plus 2. It's kind of obvious, you can tell by inspection, these look like inverse functions. One undoes the other. Like if I let x equal 7, that's my initial input, what's f of 7 going to be? 7 minus 2 is 5. And if I plug that output of 5 into the inverse function, what's g of 5 going to be? 5 plus 2 is 7. So notice, isn't that final output of 7 the initial input? Remember I said let's let x equal 7? That was the initial input. Anyway, let's show it more formally with composing functions. So what is f circle g of x going to be? Let's rewrite that in the friendly notation. And then the next step, what is g of x? We're told it's x plus 2. Plug in x plus 2 for all x's in the f function. So when I plug in x plus 2 into the f function, I get x plus 2 minus 2. And notice, simplify that. Isn't that just equal x? So notice, the final output is x. What was my initial input? Right there. That's always the input, right there, x. So the initial input did indeed equal the final output. That will always happen when you compose a function and its inverse. This input could be a number, like if this were 3, for instance, that answer would be 3. Okay, let's talk about exponential functions now. Later on, though, we're going to talk about logarithms, and it turns out, little heads up here, the logarithms and exponentials, those two functions are inverses of each other, as long as they have the same base. So that's interesting. A lot of good problems can be solved knowing that. Okay, so exponential functions, let's say the base is greater than 1. For example, given this function right here. So when you see a function like that where the variable's in the exponent, that's an exponential function. So now we're talking about a new kind of function. Like I said, this course is nothing but different functions. And what's the personality of the exponential function? We're going to learn that now. So given this function, what does the graph look like? All basic. This is a basic function because there's no transformations being applied to it. No horizontal shifts or vertical shifts or reflections or any of the other transformations out there. Then the graph will be an increasing function as long as that base is bigger than 0, and it's going to look like that. You'll always have 0, 1 as your y-intercept, and y equals 0 will always be a horizontal asymptote. Because no matter what you let x equal here, what is y going to be? It's always going to be greater than 0. Even if you let x equal negative 100, 10 to the negative 100th power is a positive answer. Okay, so what's the domain? All real numbers. That's a good thing to know about exponential functions. The domain is always all real numbers. Look at this graph. Doesn't that cover the entire x-axis? Sure. And then what's the range? Range is super related to horizontal asymptote. This is your horizontal asymptote, so the range for all basic exponential functions is going to be y is greater than 0. Okay, let's try graphing a little bit of a tougher one. F of x equals e to the x plus 2 minus 3. So notice this exponential function, because I see a variable in the exponent, has transformations. We got a horizontal shift and a vertical shift. So how are we going to graph that? Notice how powerful these transformations are. They work with all these different functions. So let's graph it in stages via transformation, starting with the basic graph. So you got to know what is the basic graph here. And I see the base e, so that's going to be my basic graph. Y equals e to the x. And all basic exponential functions look like that, and they always have that 0, 1 y-intercept. Like what's e to the 0? If I let x equals 0, isn't any number to the 0 power 1? Except for 0? Okay, so, and then y equals 0 is always the horizontal asymptote, so I would always label that in your basic graph. So let's continue. We do it in stages, one transformation at a time. So now I'm just going to worry about that horizontal shift. Remember, if you have a vertical shift, you can't go wrong doing that last. In this case, though, it doesn't matter. Order doesn't matter. Okay, what is this graph going to look like? It's going to look remarkably like the prior graph, except I'm going to slide this graph 2 units to the left. Remember, the horizontal shift is tricky. It's the opposite of what you think. So that's what I did. I slid the graph 2 units to the left. Pretty much looks like the same graph. And more importantly, what do I do with that y-intercept? Well, how does this point transform to over here? Doesn't the horizontal shift affect previous x-coordinates? This says subtract 2 from all previous x-coordinates. So what is, here's the x-coordinate 0. What's 0 minus 2? Negative 2. And leave the y-coordinate the same. So there we have it, negative 2, 1. I could do a spot check on that. If I let x equal negative 2, do I get the output of 1? Does y equal 1? What's negative 2 plus 2? 0. What's e to the 0? 1. Horizontal shifts do not affect horizontal asymptotes. So y equals 0 is still the horizontal asymptote. One more stage to go now, the whole enchilada. So now what is this graph going to look like for this function? It's going to look remarkably like the prior graph, except we're going to lower it down 3 units, because that's a vertical shift. Very honest, that's a minus, so that means you drop the graph 3 units. So just drop it down and draw away. And then let's see what this ordered pair transforms to. Vertical shifts affect y coordinates. So what's 1 minus 3? Negative 2. And leave that x coordinate the same. So negative 2 is our new point there. That's how it got transformed. And vertical shifts do affect horizontal asymptotes. Doesn't it say subtract 3 from all previous y's? And isn't this y equals 0 for the horizontal asymptote? So what's 0 minus 3? Negative 3. So y equals negative 3 is the horizontal asymptote now. Notice I drew in a dotted line. Don't be shy. Do not be bashful. Draw in that horizontal asymptote. It's a dotted line. It's really not part of the graph, but a guideline to let the person looking at the graph know that this graph here, this part here will go on forever, but never touch or cross that horizontal asymptote. Okay, now that we got it labeled good, let's answer these questions. What's the domain of this final graph? Well, the domain of any exponential function, even if it has transformations being applied to it, is always going to be all real numbers. And you can tell this graph will cover the entire x-axis. What's the range going to be? Range is super related to horizontal asymptote. And doesn't it look obvious that this graph is covering this part of the y-axis going up? Because notice this part here is covering that positive part of the y-axis, and only down to negative 3 on the y-axis. It's not even going to touch it. So that's why you got to write the range as y is greater than negative 3. Or an interval notation like that. A rounded parenthesis there because there's no equal sign in that inequality. What's the end behavior of this graph? That means immediately write down these 2 rows. As x goes to infinity, where does f of x go to? And as x goes to negative infinity, f of x goes to. And then fill in these blanks. I did it with a different ink color. As x goes to infinity, we're going this way. And isn't this part of the graph at play? And isn't that going toward positive infinity on the y-axis? Indeed. And what about as x goes to negative infinity? Where are those y coordinates going? So as we're going this way toward negative infinity on the x-axis, we're looking at this part of the graph. And as we get closer and closer to negative infinity, isn't this getting closer and closer to that dotted line y equals negative 3? So that's where that goes. And then let's find the y-intercept of this graph. To find the x-intercept, you're going to need logarithms, and that comes next section. So let's just stick with the y-intercept. So here's the, make sure you look at the final graph. What's the y-intercept? And that y-intercept's always done the same way. You let x equals 0 and solve for y. So that's what I did here. Let x equals 0, solve for y. What's 0 plus 2? 2, so we have this now. Or you can write it as an ordered pair. I know that looks like a funny answer, e squared minus 3, but that's an exact answer. You could use your calculator and type in e and square it. Remember, e is roughly 2.718, so, it's around 6, I think, So it could, it's around 0.6, but this is the exact answer. Okay, so good enough, and I'll see you next time.